panel discussion. Strosha, I can't pronounce it badly, I'm sorry, is going to moderate, and he'll introduce the rest of the speakers, but I get to introduce him. He's taken on a job as head of the Control of Complex Systems Initiative for PNNL. Let me read it because it's interesting. Internally funded research initiative aims to develop mathematical foundations for how the many diverse components of complex systems in our world collectively operate. Before coming to PNNL, he was head of research for the Department of Electric Systems at Aalborg University in Denmark. I think I'll stop there if that's okay. You can. Welcome.
Thank you very much. And so we got. I will be moderating, and I will be giving the last panel contribution. So now we got cleared up that I'm neither Paul DeMartini nor Jeff Taft, if you were wondering. Could I ask the other speakers to come up here? So we'll first give each a contribution to the panel, and then I'll try to limit the enthusiasm by the speakers so we get just a little bit of time at the end to have discussions. And I hope you will all think about how you can challenge the speakers. I would like to introduce the first speaker, who's going to be John McDonald. John McDonald is a director of technical strategy and policy development for GE Energy, the part that deals with the digital energy business. And John has 40 years of experience in the electric utility transmission and distribution industry. He received BS and MS degrees from Purdue and an MBA from UC Berkeley. He's a fellow of IEEE. He has several awards from IEEE, from Power and Energy Society and various others, and the distinguishments are far too many that I can mention them all. He is a chair. He has been elected to the chair of the NIST Smart Grid Interoperability Panel, and he's currently chair of the board. And he has published numerous papers in the areas of SCADA systems and communications, and he has co-authored 3 books. And the CV is much more extensive than that, but I don't think I have more time to introduce them. So, without further ado, please go ahead. Can I ask you to use some slides? Yes.
Okay, thank you very much. And I thought I'd kick this off with some general concepts about smart grid. And I want to zero in on 3 specific challenges that we have, 3 different areas of smart grid that I know in talking with Rafer, Tariq, and Patrick that they're going to talk about in more detail. So I think this is a good way to set the stage. First of all, when we look at this field and we put strategy together, what are the key things that are happening in general? First of all, we're transitioning from devices and systems to holistic solutions. A device, a microprocessor-based device, and a system are very much like products. And with smart grid, we have the opportunity to be more creative and look at technology components to integrate together, to interoperate. And interoperability is important, that Patrick will talk about in more detail with respect to standards. But the idea is that a holistic solution addresses the business needs of the customer. We're a product, we develop a product, and then we go out and we sell it. Okay? Success is three parts, and each of these parts is very important, as important as each other. Technology, industry standards, and policy. Right? We could have the best technology, standards based, but if policy doesn't incentivize the customer to purchase, we won't be successful. Right? Policy could incentivize the customer to purchase, but if the technology isn't standards based, it won't interoperate successfully, and it won't work well. So all three are important. Let's skip down to flexibility, grid flexibility, self-healing, and reconfigurable. So the technology that we're developing and the installation of that technology, we need to emphasize flexibility, particularly with the distribution system, self-healing, and some of this is technology, some of it is cultural. You know, cultural meaning once we have confidence in the logic, don't be afraid to close the loop and let the logic do its thing and report after the fact what it did. And don't be afraid to distribute the intelligence. We don't have to have everything come to the control center, make the decisions, and then decisions come downstream. The industrial side, not the utility side, but the industrial side of what we do has distributed intelligence for many, many years. We've been very slow to do that on the utility side. The word resiliency is very important today. We need to design the grid for, and Buck talked about this earlier with Florida Power and Light, right, about going from wooden poles to concrete poles. He said, after the hurricanes that they've had, when they rebuilt the system, they rebuilt it more resilient, right? The choices they made in equipment. So that's important. Big data, how do we manage all of the information that we have? Rayford's going to talk about that, and that's one of the areas that I want to talk about also. Having information stored in the cloud and working with the cloud. Also the use of social media. For a year now, we have a platform where we can take tweets from customers after an outage and bring those tweets information directly into the outage management system. Okay, so it's another source of information from utility customers that what the bottom line is, it helps us assess the situation more quickly, right? And know how to restore electricity then faster because we have better information up front. We don't have to rely only on customer calls or interfaces to changes of state on the SCADA system. And then the convergence of IT and OT, information technology and operations technology, which Rayford will talk about, and I want to talk about a specific case also. So this is what's going on. And I've been working full-time in the field of power system automation for 40 years. So I want to emphasize the fact that the smart grid, it's not something that we've just started putting intelligence to the grid. Many of us have been doing it for our whole careers. So what I show in light gray here is what we've been doing for some time. It's not new, right? We've done a lot of work leading up to 4 or 5 years ago with the stimulus funds and particularly in 2007, it was the Energy Independence and Security Act, where Title 13 first and foremost defined what smart grid is for the United States. Okay, so it was federal legislation in 2007 that defined smart grid for the U.S. What in light green here is what we're doing with smart grid, the new things that we're doing. And I want to zero in on 3 of these in particular. But this is very good from the point of view of getting a good perspective on what have we done and what are the new things that we're working on now going forward. What's important, I said, is solutions. and you can get an idea of what I mean by solutions, just take a look at the light blue boxes here. This is a technology roadmap for 6 different solutions that we've developed at GE. The driver for this was the strongest business cases for utilities, okay? And it was taking technology components, some that we had, some from third-party companies to fill our gaps. But the important thing is, all of these technology components must work together, right? That's why industry standards are so important. Take a look at the light blue boxes, just for distribution. We have software applications in the control center. We have systems, distribution management, outage management. We have hardware and software at the substation level, and hardware and software downstream of the substation on the feeders, okay? There's a lot of individual components here, software, hardware, firmware, that all must work together. Okay, that's just an example. All right, so that's what I mean by an integrated solution. These light blue boxes today provide the strongest business case for electric utilities of any of these solutions we're talking about. The predominant spending today has shifted from smart metering to the distribution system. Second is probably monitoring of transformers. The average age of a transformer today in the United States is over 40 years old. And for a small percentage of what that transformer value is, we can get online monitoring and diagnostic technology that monitors the health of the asset on a continuous basis. Okay? It's a very strong business case. So let's look at real briefly, three areas. One is when Hurricane Sandy hit the Northeast, we had a lot of discussion about how can a utility best prepare their grid to be the most resilient to withstand an extreme weather event. And we said there's 5 key components that the utility should invest in first. Each of these components standalone provides value, but it's the integration of the 5 components that provides the greatest value. We're talking about smart meters, AMI communications, metering communications, geographic information system, outage management system, and distribution management system. For instance, in addition with the meters and the communications with the meters, we get the meter readings, but we also get the voltage at the residential home, which is at the end of the feeder, which is important for our network model on the distribution management system when we do volt reactive power control. The meter also gives us the last gasp communication. When electricity goes out, the meter has enough energy in it to make one last communication, and that tells the outage management system, I'm without power beginning right now. Okay? So the utility knows exactly the situation and when it occurred, and each customer that's without power. The geographic information system provides the network model for the outage management system and DMS. The DMS provides status changes to the OMS. Whenever a breaker trips and a feeder is de-energized, we send that information to the outage management system. It knows all the customers connected to that feeder and the fact that they're now without electricity. And customers, in addition to calling in, we empower the customers to use social media to provide additional information through tweets, as an example, and photographs. Customers can take a photograph of a tree that's fallen on a power line, right, with location services turned on, and send that to the utility. Secondly would be impact of high penetration of rooftop solar PV on the distribution system. I wrote an article in Power Electronics Magazine, August 22nd, 2013, working with San Diego Gas and Electric. They have 35% penetration on several distribution feeders of rooftop solar panels. Look at the voltage volatility on that feeder. In the morning when the fog burns off, fog on the Pacific Ocean burns off, and those 35% of the homes on that feeder go from 0% sun to 100% sun instantaneously. Okay? This article, I have waveforms that we've gotten, voltage waveforms from the utility that we've analyzed. 3 things. 3 new applications of power electronics. One would be the online tap changer and the transformer. A mechanical means of control in this new volatile world just don't work anymore. We have a prototype of a power electronics based tap changer, as does Siemens, ABB, Areva, and Schneider. Second is grid edge controllers, power electronics based, that we install in the low voltage network, where the volatility is coupled into the grid. Okay? Companies like Vrentech in San Jose, California have these new grid edge controllers. Third would be increased capability from the power electronics and the inverters. We amended the IEEE standard 1547 the last part of last year to give us the capability now to use inverters to compensate for voltage and reactive power. I was in Brisbane, Australia last year, and the state of Queensland passed policy that greatly incentivized residential customers to put rooftop solar panels, and the utilities weren't prepared for it. So Energex and Ergon are backpedaling as their feeders now have 30-35% penetrations. Volatility of the voltage is beyond what they ever imagined, and they don't know what to do. They're backpedaling. There's a good article in the Intelligent Utility magazine, just November, December, called The Death Spiral. Okay, if you're interested in it, it's a good resource. Last topic is enterprise data management, bringing OT and IT together. Situation we have today, grid operational systems, separate from the intelligent electronic devices, separate from the data repositories. Where we want to go is a federated data mart in the IT side of the utility. Overall data manager, bring together the data that's in the systems, the operational, non-operational data in the microprocessor-based devices, and logically link all the existing repositories into a virtual data mart type setup. And I'll finish with this. This is the value proposition, is that this is our substation architecture, taking advantage of the data in these devices. This is the different types of data that exist in the enterprise. More importantly, there's 25 to 30 groups, business groups in the utilities that can provide more value to the utility organization if they had access to the data on the OT side. And I know Rayford and I talked about this. There's a disconnect between OT and IT in the typical utility, which means, bottom line, if you spend $5,000 for this device, the way that it's being put in the field today by the typical utility, they're realizing no more than about 20% of the potential benefit that that device could provide the organization. There's 80% of untapped benefits, and we could go into detail about how to realize those untapped benefits. And it's not rocket science. A lot of it is cultural, not technology, but getting siloed groups to work holistically together. On that basis, let me stop and turn it over back to the moderator. Thank you.
Thank you very much. And we will do the questions at the end for the whole panel, individual or at last to the panel. So the next contributor here is Patrick Gannon, who is the Executive Director and President of the Smart Grid Interoperability Panel. Previously, he served as the President of Warning Systems Incorporated and as President and CEO of Oasis Open, the Internet Technology Standards Development Organization. He's been appointed in 2006 as high-level advisor to the United Nations Global Alliance for IT Development. And he has also served in the 5 years past that for the United Nations Economic Commission for Europe as a chairman of the team of specialists for Internet Enterprise Development, which advises government and transitional economies on best practices for electronic business. So, please.
Let's see if this...
Yeah.
Oh. Great. Thank you very much, and thank you for the introduction. And it's not only my pleasure to be here, but also on a panel with all members of our consortium. I'll go into a little bit there, but it's great to be in good company here. What I wanted to kind of brief you on is the work of the Smart Grid Interoperability Panel and how our role is accelerating adoption of a smart grid, and more importantly, an interoperable smart grid. When we talk about interoperability, one of the key questions is, well, why is it needed? And one of the major things is to consider how you go about reducing that distance for integration and the benefits of having interoperability within the smart grid system. So one of the key things is reducing the cost, both of installations. When you think about connecting systems, engineers can design interfaces for almost anything, whether it's a hardware or a software interface. But if it's a one-off, that's going to be a whole lot more costly than if you build a standard interface with hardware or software that can easily connect. You know, we're nicely able to enjoy the benefits of a USB connector and plug in all sorts of interesting things. The same thing occurs with software standards. So it lowers the cost for that. Also creates a defined point whereby people can engineer and design around that and design to that, which makes it much more easy to create a lot of new opportunities and new applications that can come about from that. And then the automation of components that easily adapt to the various interfaces that are defined there, as well as an upgrade path. And this is an important consideration in the utility industry, where it's coming from a background of investments in assets, typically on a 30-year or longer basis. And so with the advent of smart grid, as John McDonald was pointing out, is you have a lot of new technologies coming in, and having standardized interfaces allows you to actually extend the life of legacy systems by being able to plug in new applications, as opposed to having to take out, get rid of something old and replacing it with an entire new thing. Oftentimes you can do a stepwise kind of upward integration going forward. Also, the abilities to actually create a more competitive environment, because when you have standardized interfaces, then you can actually create competition among the different applications to compete more on features and support, etc., as opposed to competing on proprietary interfaces. And ultimately, the value to the utilities is the ease of adding more features and benefits going forward. And so with that driving the benefits for interoperability, there was a recognition that there was a need to bring about those kinds of benefits into the energy industry. And so with that was the launching of the organization called Smart Grid Interoperability Panel. And as John McDonald mentioned, in 2009, with government funding, a project was initiated by the Department of Energy and National Institute of Standards and Technology to form the original SGIP, which was run as a government project, and a year ago was spun off as a non-profit corporation, and then I was hired as executive director. So that's what's allowing us to go forward. And so within the Smart Grid panel here, we're helping to ease the pain of all that growth by getting vendors and utilities and regulators together, much like the goal of this workshop here was bringing together interdisciplinary experiences to collaborate. Well, and that's exactly what SGIP is all about, is the collaboration, that uniqueness of having that kind of collaboration, where by engaging the stakeholders from different backgrounds can come together and focus on specific needs and the practical implementations of those. And then with that, helping to lay out the path forward for interoperability. And so one way of viewing this is that really our goal is, as a kind of a conductor of an orchestra, helping to orchestrate all of the players in power grid interoperability. And that's a way that we work. We don't, as I say, you know, we're not the guy who writes the music. We're not the one who writes the standards. We help to define requirements that then can be passed off to standards organizations. So with that, our goals are basically to work with our members to help reduce the risk and cost. And in fact, this is something that's been vitally important as we've interacted with the regulator community, because that's ultimately what they look at when they get rate proposals coming in from the utilities is this going to lower cost or risk? And that's one of the judgments that was fed back. And when asking about interoperability from a regulator standpoint, they're saying, does this interoperable solutions lower the cost or the risk? And that's really what helps to drive our function going forward. And with that, we've got people working on the architectures that helps to build the roadmaps that then enable the standards to fit into those roadmaps. So one way of looking at that is we are really a collaborative, transparent, and trusted forum that helps to share information about the standards and also the practical implementation of those standards. A snapshot of our membership base, around 200 companies, both the utilities, and so Duke Energy is certainly one of our investor-owned utilities, but we also have municipal and rural electric co-ops participating, as well as the different ISOs, TSOs, manufacturers, examples with GE and Honeywell and many others, as well as software companies such as IBM and Microsoft and others like that who have a lot of software solutions. Associations for many of the industry groups, as well as the standard development organizations, and then a wide range of governments from federal, international, as well as state and local. Examples of some of the federal organizations is not only those who are driving the electric market, but also in the energy space with a number of the national labs. And this becomes particularly attractive to the academic environment. Here's also where a lot of the research that goes on and researchers coming together to talk about what's new and what's feasible, but having that opportunity to interact with the utilities and with regulators to understand what will be the boundaries and parameters for actually moving forward with some of those research ideas. Within our academic community, these are some of the universities and different kind of research departments that are heavily involved. And we would invite those here who come from academics environments to talk with us and see how you too can interact and be part of this kind of activities that we're doing within SGIP. And we find that a number of these groups bring expertise, and that's one of the things that becomes highly valuable to our utility members, as well as even some of the regulators who, when they have to go do research, they know they can ask questions, they can look at documents and white papers that have been produced by these groups. And we also have international outreach. So we have agreements, liaison agreements that have been prepared working with Korea, Japan, European Union, as well as in South America with Ecuador, Colombia, and Brazil. So this is just part of our international outreach, primarily focused around alignment of the standards, because we want to make sure that the standards that do get adopted are within the realm of the international standards, such that products that are built to standards can be sold within many different markets without having to, again, re-engineer those. Give you a quick idea of some of the activities that our members are involved in. This is a snapshot of the what we classify as our member groups, and there's three primary categories. We have our domain experts, and again, this is where a lot of the researchers are involved. These are kind of long-standing groups, and as you can see, they focus on specific sectors of the smart grid domain, in terms of whether it's building the grid or vehicle to grid or the renewables area. And that distributed renewables generation storage is one of the most active groups with, I think they have like 7 subgroups doing a lot of research into interconnection of renewables, et cetera. The priority action plans are the projects that get ramped up from the research that goes on where they've identified a market need or they identified a particular gaps that exist in terms of what standards are available, and would come forward with proposals to actually go off and put together a project. Oftentimes these are the requirements gathering stages that then hand those off to the standards organizations. And then we have 4 standing member committees that are really part of doing the evaluation of various standards that then lead to what we call entries in our catalog of standards. So they do the review of existing standards as to whether it fits within the smart grid architecture frameworks, if it can abide by the different cybersecurity guidelines that are out there, as well as can it be implemented and can it be tested. And so these are valuable reviews that go on of the standards, and then a whole range of products that are generated from those activities. A couple of the example deliverables that are coming out. We've got one in the home to grid market that did research into if you're trying to pass energy information into a home energy environment, does it have to be through the internet? Because there's some geographies where they don't have internet coverage. And they went and looked and said, yes, you can use the FM broadcasting data side channel as a way of transmitting energy. So there was a white paper that was done as a response to a specific request there. Our implementation methods just published the work on the common information model, how that was implemented at the DTE Energy. And that was very helpful, lessons learned. It went into the analysis of some of the information architects and what experiences they had around that. And then we just published this user guide for the original cybersecurity guidelines that were developed in 2010. This is kind of a high-level user's guide that's becoming very helpful for executives of utilities or regulators to begin to understand kind of the 8 steps to going through and developing a risk management process for a particular organization. So these are recently published articles. And then coming up, we have groups that are working on another implementation case study, looking at cybersecurity in terms of the breadth and depth of defense, and also doing assessments for cloud computing and what the impact is on utilities and the smart grid. In the distributed renewable space, actually looking at a classification, categorization of the different use cases. Because as somebody when I was talking with in the utility space was pointing out, there's, especially those utilities that cover a broad geographical range across different types of use cases, the way you use the distributed energy resources varies. And so the actual kinds of object models that you might use, you need to have an easy way of determining which model that would apply in different scenarios around that. Again, looking at the various ways that microgrids can be deployed and the impact of that. And so these are some white papers. There's also work here on the areas related to transactive energy. And when you talk about the interaction of smart appliances in the home energy system and responding to transactive pricing information, what's going to be the impact? So these are some areas where people are actually taking that research, doing the examination of that, and talking through some of the implementation scenarios around that and writing papers around that. Folks are looking at electrical storage versus thermal storage. And so you can see many opportunities where we reach out to find experts in key areas who are doing research, and then work with those people who have the practical knowledge of how is this going to actually roll out within a utility, and how would the vendors and software systems support that kind of ideas. So this is just a good idea of the variety of work that is going on within the Smart Grid Interoperability Panel. And when you begin to then see how all of this work impacts a utility operation, it's not just at the distribution end of smart meters, but throughout planning cycles, dealing with customer service as outage management systems, and a whole variety of areas that are affected. And so this is why the work of the driving interoperability is so important, because it affects so many parts of a particular operation. And I'll end there, and then we'll come up with questions and answers later. Thank you.
Thank you very much. The next speaker is Tariq Samad. He's a corporate fellow with Honeywell Automation and Control Solutions based in Minneapolis, USA. He has been with Honeywell no less than 20 years, during which time he has contributed to and led automation development for applications in electric power systems, the process industries, building management, automotive engines, unmanned aircraft, and clean energy. His research interests relate broadly to automation, intelligence, and autonomy for complex engineering systems. He is the president of the American Automatic Control Council for the next 2 years, and he has served as the president of IEEE Control System Society in 2009. He's a fellow of the IEEE and currently serves on the editorial board of IEEE Press. He represents Honeywell on the Global Carbon Capture and Storage Institute, and he's a member of the board of directors of the Smart Grid Interoperability Panel. He also has a BS degree in engineering, applied science from Yale, MS and PhD degrees in electrical and computer engineering from Carnegie Mellon.
Thank you, Jacob, and my pleasure to be here, and thank you, Sean, for the invitation. Okay. So, it doesn't matter. So I'm going to tell you about demand response, and so continuing the focus that we heard in several of the earlier talks on the facility side of the smart grid. And I'm really not going to talk about the research that's being done so much as what's really happening today in industry in terms of actual implementations and some pilot projects, and some of it is, I think, quite exciting. And in talking to the research community, it seems that there is actually a good need to sort of connect the practitioners and the researchers better than they have been connected. Let me start, though, by this picture, and the question is, what does the smart grid mean to you? And kind of depending on where you come from and what your interests are, the answer could be different. But from where I come from, it's very much a matter of demand-side integration. And in fact, what defines the smart grid to a significant extent in my mind is in contrast to the traditional vision of the power system, where we were able to control generation to make up for uncertainty or variability in the loads, relying simply on signals that were coming through the power system itself. Well, now we have, with renewable generation, significant uncertainty and unpredictability on the generation side as well. So conversely, we have to similarly be able to manage our loads and our facilities in the same way conceptually that we've traditionally talked about managing generation. And in order to do this, we can't just rely on the electrical wires. We have to have a separate information and communication infrastructure. And as you look at what it means to be doing grid balancing with renewable generation, you have to, and again we heard a lot about this already, you have to think about, well, has the peak management problem gone away with renewable integration? No, it hasn't. In fact, in many cases, problems have been exacerbated. This picture isn't even showing the volatility that's there in wind and solar, which is substantial, as we've already seen. But you could have exacerbated ramp effects as well, and ancillary services need to come into play. So the whole grid balancing issue is actually further compounded, one could say, with renewables and another call for demand side issues. So I want to mention couple of interesting projects that are underway. Some of them are fairly well advanced. This is in fact quite well advanced. It's a project that we had with the Department of Energy, a smart grid investment grant, where we are in the process of, and I think this is mostly done now, we got a short extension to complete it, 700 buildings, commercial buildings in the Southern California area, Southern California Edison, where we're doing automated demand response through these subsidiaries of Honeywell. One is Akuacom. So Honeywell acquired this company, Akuacom, a few years ago. They provide this server, the demand response automation server, which is the system through which signals from the utility are communicated to aggregators and to individual facilities in order to implement demand response actions. And the other piece, which is another acquisition of Honeywell from some years ago, is Tritium. And they actually have this very cool technology which, in effect, overcomes this proprietary systems bias that otherwise, as a building owner or operator, is likely to tie you into one vendor. So, if you're Honeywell is certainly a well-known building automation system provider, and traditionally our automation systems have had our own protocols in them. The same is true for all other building automation systems. Once you get a building automation system, any extensions you make, any enhancements you make, any new functions that you need to plug into those, in the past, more or less required you to stick with that vendor. So what Tritium provides is a protocol box that actually talks all these protocols and interoperates among them. So in this project, these 700 buildings, some of them have Honeywell building automation systems, some of them have Siemens, some of them have Johnson Controls, and they all work in a uniform way, serving up web pages, and these buildings can be operated, commissioned remotely, and demand response signals can be given in the same way, and communications to and from can happen together. So a total demand response capacity of 80 megawatts, all being done through automated demand response and through a particular standard that we'll mention. This is not just a US thing. We are doing projects all around the world. This is China's first automated demand response pilot project in the Tianjin development zone. And again, it's a similar kind of picture here as well. And China has its own priorities, of course, for the grid and own issues with the grid. But demand response is actually quite important there as well. And managing demand in general, especially in an economy that's growing as fast as it is even more crucial. So a lot of interest there too. The third project I wanted to mention is something that started relatively recently, and this is moving away from thinking about demand response as just sort of a let's manage peak load, let's reduce consumption during a hot summer day kind of model, to doing ancillary services. And this is in particular for frequency regulation. So this project is with the LA Air Force Base in Los Angeles. And the LA Air Force Base is replacing all its fleet vehicles, I think there's over 40 of those, with electric vehicles. And whenever these electric vehicles are parked, they are plugged in, and they're under control through, again, this OpenADR, this automated demand response system, for frequency regulation and just doing charging, discharging continually. And this actually makes a lot of sense from many points of view, and including from an economic point of view. The California ISO gives good money to be able to provide the service, and they may not even need the service very much. But I think the number is here for in 2011, for example, frequency regulation revenues from KSO were $15 per kilowatt, and the individual vehicle can provide up to 15 kilowatts in these cases. So very exciting project. This is the first example of the DoD doing something like this, and their vision is they want to do this in every military base in the country if this works out, and good money is to be made. And we're now talking with them about, well, you know, if you can do something like this, now you should start thinking about all the vehicles in a city and develop statistical models about driving patterns and where these vehicles could be plugged in, and you could be providing ancillary services and regulation services in localized regions depending on where the cars are, and relying on these electric batteries in these vehicles, not just for mobility, but also when it makes sense for grid balancing. So those are some examples of some interesting projects, and all of this is really being enabled by standards. And one particular standard that's becoming sort of de facto for automated demand response is the OpenADR architecture. And this is actually the OpenADR standard. And actually, Patrick, who just talked about the Smart Grid Interoperability Panel, mentioned demand response and other functions that the SGIP is helping facilitate, and other standards it's helping facilitate. So OpenADR is one of these, and in fact just this week the OpenADR 2.0 profiles A and B were approved for inclusion in the catalog of standards that Patrick mentioned. There's actually another related standard that's quite useful for demand response, especially in residential facilities, SEP2, that has also been approved at the same time. So good progress on the standardization front with demand response too. And in fact, in both these cases, OpenADR as well as SEP, internationalization is in progress too in the case of OpenADR with IEC. So OpenADR actually provides sort of a hierarchical network and defines what information and communication needs to happen for these to and fro demand response signals. So it can, for example, target localities, whether it's in an electrical sense or in a geographical sense. It can target specific kinds of assets. So you can give signals such as, I want this demand reduction to happen just with motors or just through thermostats. It also has a privacy aspect built into it. You communicate through intermediate nodes, and you as the utility or as a higher level node does not even need to know which is the ultimate customer that is finally serving this demand response request that you have. And now it's being extended, has been extended in fact, to ancillary services as well as to distributed generation and storage as well. So really the standardization is really crucial, and it's enabled and is enabling the pervasiveness of automated demand response. Finally, I thought I'd just mention a couple of interesting research issues, especially for the academics here. This is things we're working on that I think a lot more needs to be done, but in fact this work is happening in our lab in Prague in the Czech Republic, which is another big place where we're doing a lot of this sort of work. So one issue is, if you're a utility and you want certain level of reduction in demand, how do you know what demand response signal to give out? Right? There's going to be some uncertainty about the response that you'll get. How do you know, and if you're a building owner, how do you know what kind of capability could you provide for demand response? If somebody says, if the utility says to you, give me this reduction, what changes do you need to make to your consumption pattern to provide that? And again, going back to the utility point of view, one thing that happens with demand response and demand response implementations is that it's not just that you're reducing the consumption over the time period you want to reduce consumption. It's also that there are lead effects and there are rebound effects. Often there's a peaking effect before that demand response hits. Often after the demand response event is over, there's a rebound effect. So we need to be able to model these things too if we want to do demand response in an optimal way. So the idea here, in fact, the one we are pursuing, is to really think of this as a data-centric forecasting issue, because data is being collected in buildings all the time. As demand response events happen, their data is collected. You can now think about developing building, I'm pointing to the wrong thing, building models where you can take into account building parameters, environmental parameters, and get predictions and forecasts of the baseline profile as well as the affected load. So that's the modeling piece, and once you have the modeling piece, you can now think about putting together your optimized demand response portfolio and signal. So in the current approach, really what utilities have to do is they have to collect various bids that they have and stack them up to figure out, okay, for this level of reduction, this is how I can achieve it with these customers. Well, now you can actually have a more accurate and fluid forecast there, and you can figure out optimally how I can get the specific kind of response and reduction I want, taking into account these lead and rebound effects. Finally, as a research challenge, when it comes to many demand response applications, there is a human in the loop. There are opt-in and opt-out sorts of capabilities that are included in these standards and that are going to be important. Now when you have a human in the loop, you have to think about there's a loop being closed around the electricity, of course, but there's a loop being closed around prices, possibly mediated to some extent by the human. You can have instability issues either on the electrical side or in the market side, and they come together. So how do you do that? And when there's been a lot of interest in trying to model the human consumer, the human energy consumer, and there are lots of complexities with that as well. You give people information about their consumption, and sometimes for a week or two they're really eager to see what they're doing and making changes, but then fatigue effects come in. There's also learning effects that are involved, and that's really also the sort of activities and complexity that needs to be taken into account. I just thought I'd end with sort of a look back, and John mentioned John McDonald, that he's been in this area for 40 years. I actually did some research many years ago, but really my active recent involvement is about 5, 6, 7 years ago, something like that. And this is a slide I was using 5 years ago or so, which was motivating the need for the smart grid, right? So we were saying at that point, we were looking at our reserves to production ratios for oil, natural gas, and coal. So how many years of production do we have given the reserves we know about? And we were saying we had only 10 years of natural gas and 10 years of oil left in this country before we ran out of it, right? And that was true of Western Europe as well, more or less. And then we were looking at prices, and here's 2006 or so, and natural gas prices are something like $7.5 per million BTU, and the projection from DOE was it would stay at that level, right? So we wanted to get away from fossil fuels for these reasons. There was, of course, also the environmental aspect. CO2 reductions was a big thing, right? So here's the 2013 update. We said our natural gas reserves to production ratio, which at that time we said was 10 years, should have been 5 years now. Well, now it's 105 years, right? Natural gas price has in fact halved in the course of this time. And you may say, well, okay, but what about CO2? Yeah. Well, the situation in CO2 is really very optimistic as well if you just think of it from a US point of view. We have the lowest per capita CO2 emissions since 1964. Yeah. So does that take the wind out of the smart grid sails? And that's actually a question I've been asking myself, and I know people who I rely on to support activity in smart grids, they're asking that question too. I think the answer is it has not. That in fact, the arguments are still very much there. For one thing, half the CO2 footprint of coal, which is what natural gas gives you, a lot of CO2. And then what's happening with this coal that we aren't burning? It's not just sitting in the ground. We're exporting it, right? So US exports to coal increased 100%. Exports of coal to China increased 100%. Exports of coal to the UK increased 70 some percent. Many CO2 emissions have increased in many economies, as was mentioned in Germany, for example. Natural gas prices for the US are quite low, but they're not low at all in other parts of the world. Natural gas isn't something that's so easy to export, right? So there's good reason to keep the pedal to the metal, as it were, in this area. So let me just stop there. I don't think I have anything more to add on my conclusion slide. So
Thank you very much. And next presenter is Ryford Smith, who is Director of Smart Grid Emerging Technology for Duke Energy. In this role, his team is responsible for developing and assessing new transmission, distribution, information technology, and telecommunications technologies for the smart grid, including initial business case development and global project management for technology development. For the smart grid and global project management for technology development initiatives in the United States, China, South Korea, and Japan. Ryford Smith has 21 years of experience in the energy industry, including various roles in legal, customer management, efficiency, pricing, and rates, product development, wholesale, deal structuring, mergers, and acquisitions. He's a native of Savannah, Georgia, and there he has earned the Bachelor of Science degree from the University of Georgia. He has a Master's of Business Administration degree from Darden Graduate School of Business Administration at the University of Virginia, and he's a Juris Doctor from the Charlotte School of Law. He's a licensed attorney, and he's a member of North Carolina Bar Association. He's published several papers on energy efficiency, asset optimization, and price forecasting. And he has many more merits, but now he is working. I think, okay, I can mention also he's earned 6 Sigma Green Belt certification. He's a recipient of the Southeastern Electric Exchange Industry Excellence Award in the categories of rates and regulation. And yes, okay, so many more merits, but I think that will be it.
Thank you very much. And so I would like to reiterate first my apologies for being a University of Georgia graduate and yet being here on the University of Florida's campus. I realize that our schools haven't necessarily had always the most generous and open relationship, but here's my olive branch. That being said, I am an attorney, which means I don't know why, but they invite me occasionally to speak at these functions. And I was joking in front of a bunch of attorneys that my punishment for being a recovering attorney was that I would have to manage a group of engineers. And they dutifully put up with me and my silly questions. That being said, what I thought I'd talk today about is a little bit about what we as the utility see in terms of the future of technology. And with that, I thought I'd make this a bit of an interactive discussion. First off, because we're really just after lunch, and that's always the worst time for people because they always get tired after that. So if you all don't mind, please stand up for just a moment. Everyone, please stand. Thank you very much. I'd like to show you that this is actually a demonstration of centralized control. Thank you. Please sit down. It's also a demonstration of, though economists and engineers debate about things, lawyers are the ones that are really in control.
And church.
That's right. You'll all be getting my bill later. It's quite expensive. So first, who is Duke Energy? We're the second largest utility in Florida, but we're actually the largest in the United States, and we're also the largest generator in the Americas. We've got a lot of assets in a lot of different places, but primarily in the Midwest and the Southeast. We're headquartered in Charlotte, North Carolina, though we have offices in all of our areas here. Wow, boy, the slides kind of look funny. But so a bit about my group. So I run the Emerging Technology Group. What is that? That is essentially the research and development function. So if you think within Duke, we have a function that's job is to develop new technologies. That's what I run. There's another group, their job, grid modernization, they deploy it, and yet another set of groups, and they operate the system. We did that because, gosh darn it, if you put all of us together, we all kind of lose focus. We either want to do one of the three functions, but never all three or all three of them well. So that's why we're divided up. A bit about the observations of the future, and this is probably not going to come as any surprise, but people have spent a lot of money on meters. We hear a lot of talk about meters and smart meters and aren't meters great. I don't know about y'all, but I'm really tired of hearing about meters. The world is so much more than just a meter, and there's so much more to do. And utilities are just kind of waking up to this fact, and they're all starting to move beyond the meter. Second is that we see this convergence between information technology and operational technology, and that it's really affecting how we run our business and how we operate the grid. Of course, a lot of stuff that we're stuck with today is because we live in silos. Most utility employees tend to work in one area and one alone for 30 or more years. Unfortunately, I've spent my career in just about every portion of our business, which makes me completely bizarre, but it also means that what we are trying to do is mix and match all those different functions together so we can actually solve the problems, because they're not really unique to any one area. They're really a cross-functional issue. Big data, big problem, but it's also, every time I hear the phrase big data, especially when it comes from a vendor, no offense, I hear the cash register go cha-ching, and that tends to make me nervous. It makes me check my wallet. What we see is a lot of people hyping like, hey, big data is really important. I'm like, I get that. But they're always like, big data is really important. Go chase my widget, my one little widget that does this one thing. And what utilities don't yet have is a holistic perspective or strategy as to what to go do, and we're trying to figure that out. And you'll see some of what we're trying to do here in my slides. And then last but not least is that OEMs and utilities are really trying to struggle how we move from this centralized system, the one I so aptly demonstrated earlier, to a distributed process. And that's really more, as we said earlier, that was a change management function, even more so than it was a technology issue. The technology is actually there. It's getting people to believe in it and do it that's really the hard part. So with that, we have a plan. Believe it or not, we do have a plan about what we're trying to go do, and it really consists of 5 things, which is, wow, hard to believe, but have a standards-based and modular grid modernization platform, something that's interoperable. Second, make our systems more efficient, which means spend less money and spend less of our customers' money. Third, use tools or create tools to use data and analytics. Fourth, enable telecom technologies, and I'll explain that here in a minute. And then last but not least, enhance our security, because nobody likes to be hacked. I once gave a presentation to a bunch of Chinese folks from Chinese utilities, and they were really jet lagged after having flown all the way from Beijing and Shenzhen and Guangzhou. And when I was talking to them about the strategy, they were really kind of falling asleep. But when I got to security, they all perked up. because it's not just a US issue, it's an issue across the world. Nobody wants their grid to be hacked. If you turn off the power, we go back in time to the Stone Age. It's the fastest way to anarchy, and clearly all of us want to protect those assets. So it's a very important issue. Okay, so how many people here have heard Metcalfe's law other than those who are reading it right now on the screen? Okay, Metcalfe's law states, as it says here, the value of a network is directly proportional to the square of the number of compatible communicating devices. So what does that mean? Well, if we think about that relative to the electric grid, it's really a simple business model. Supply, demand, and some pipe that connects the two. And what we're really trying to do is create the most efficient transaction between those two. But what we're really doing today is we're trying to turn that pipe into a network. And that network has a lot of value. So I hear a lot of people talk about death spiral, or about getting off the grid, and I think, well, that really goes contrary to old Metcalfe's law, which says that actually being connected is actually more value than not being connected. And so it's our challenge as the utility, as the network here, is to make our network as efficient and as valuable to both the customer and the generator as possible, so we stay relevant. So with that, this is where we see this IT-OT convergence, which is to say we see the electric grid today, that's the OT, the operational technology. And of course the IT, the software side. And then the telecommunications here that really connects the two. And of course, we don't really understand it well, so we can look actually at another industry that's undergone a similar convergence to figure out where we're going. We'll look at, say, telecom, which has hardware and software. And gosh darn it, telecommunications too. And so when we look at this, we can go, okay, well, I see what they're doing. How can I apply that to me? Because after all, we all move electrons around. We just have very different amperages, right? I mean, I may be an attorney, I may not be able to do math, but I can figure that much out. And so does anybody over the age of 30 remember these devices? Well, I do, sadly, and of course that dates me. Because I remember when they were new and cool and hip, but they don't exist anymore, right? They've all disappeared, and they've turned into that, or at least that version of that. And what happened? Well, first off, when we have a smartphone, we've got all these multiple functions, and how did we get that smartphone? Did somebody create the whole thing from start to finish, the IT, the OT, and the telecom? Well, no. We have multiple people creating all of those things. Why do they work? They work because they're based on standards. And they allow third-party systems to be developed and deployed on them. That's what's most valuable. That's what unlocks the value of this system. One of the nice things about telecom that informs us a lot about our future relevance, which is, remember all these companies? 10 years ago, these guys were the ones that were number one in their industry. They were the big dogs. They were making smartphones. Well, these versions of smartphones, I should say these are the old handsets that did one thing. They made phone calls. And boy, were they good at making phone calls. But you know what? All but one of them are gone. Why? Because what happened in telecommunications is the same thing that's happening to us in the electric utility industry, which is to say, the one company, and then the other ones that adopted it, that saw the future and said, you know what, we need a standards-based solution. We need to push intelligence to the edge. We need to open up our systems, unlock them for third parties, to develop new apps, new capabilities, new systems that we can't even think of today. And those companies that embraced it, and the one from the old area that did embrace it, they survive, they grow, they thrive. Those that didn't are gone. I tell that to my industry, and I said, do you want to be a railroad? Disliked, hated, but a necessity? Or do you want to be a telecom company? Do you want to grow and thrive and provide value to your customers? Because that's the pivotal choice we have to make right now. And right now, I view it as what we're doing with the smart grid technology is making that choice, enabling one or the other future. And I don't know about y'all, but I like to have a job. I like to put food on the table. My daughter and her fetish for princesses is not going to be satisfied if I just cannot keep having a job. So I would like to grow. So that being said, this is what our grid looks like today, which is to say it's a mess. It's proprietary, it's siloed, nothing works well together. As a matter of fact, the systems are anathema to working well together. They hate working well together. And so we have all of this stuff, and what we're trying to do is make it work together. And so what are we doing? Well, we're essentially developing the smartphone for the grid. And today, what Duke is actually doing is connecting all of these assets here to that one device. And now that one device is a reference design, meaning multiple vendors can build those assets to it, just like Qualcomm does. Qualcomm doesn't actually make chips, they make reference designs, and people make things to that. We're doing the same thing. We have this, what we call a communications node, and it connects to assets in the customer's premise, meters, transformers, line sensors, you name it, everything here in the transmission and distribution side, as well as generation and continuous emissions monitoring and weather sensors, all of it. And we use all of that to first connect and route data back to us. Now, that's a good first step. But what else can we do with that smartphone? Well, we can build applications for it. We can build intelligence into the grid. Now, I had once had a vendor tell me that that was a really great theory. And since I was a lawyer, they were going to use small words. And they were going to tell me there was no way we could do all the advanced analytics that was envisioned out there in the grid, because gosh darn it, these are all little dinky computers and they're just not that smart. And I said, okay, well, we'll do some math. Okay, one node, it's not very powerful. But in our test area, I've got 3,000 of these things. Well, what does that look like when I compare it to, say, a supercomputer? Like, I don't know, Deep Blue. I played chess, won, beat Gary Kasparov. Well, gosh darn it, they look a lot alike. Well, and I said, well, in our Ohio deployment, I got 150,000 of these things. Okay, stupid math. How big is that? And what does it look like relative to, say, the Watson supercomputer that played Jeopardy and won? Gosh darn it, they sure do look alike. And then if I were to do it system-wide, what would happen then? Well, then I went down to our IT center and I wandered around our data center, and of course they immediately spotted me. They said, you do not belong here. And I said, well, I agree. But I was looking for a supercomputer that could play Jeopardy or chess. And you know what? Gosh darn it, we didn't have one. We didn't have any. We had some blade servers, we had some neat stuff, but it wasn't nearly as powerful as that. And so what that tells me is that what we have is an opportunity to build a very intelligent grid, and we're really just scratching the surface of it. That 20% that got mentioned earlier. Now, I was giving the same presentation to a bunch of Duke executives, actually, and my boss's boss raised his hand to me and said, Rayford, look, what you've got there is an over-engineered solution. Right. And being the good attorney that I am, I picked a fight. I said, I'm sorry, that's an underutilized asset. Now, which of us is really right? Well, actually, we both are. Because if all you ever do is use this system to read meters, you spent too much money. On the other hand, if you use it to really enable all the intelligence and capabilities out of the system, you're underusing it. So we're both right. Hopefully I'll be right in the long run. So a bit about how we do control systems today, and those of you who are electrical engineers will actually recognize this. My apologies for the rudimentary, like I said, I'm not an engineer. So here today, if we see a rapid swing in production, a sensor or a meter or something, we'll pick that data up and we'll route it back. It'll go through a head end piece of software that kind of takes that from that system and translates it. And then we give it to another system that then adjusts that and figures out what to do with it. And it goes and sends an answer back. What we're doing today is actually putting it to the node, putting the intelligence there, and then updating the model. This solution is far more efficient. It reduces the amount of data traffic. It's less costly. It reacts much, much, much faster than today. And it doesn't have to be proprietary to any one vendor. So how are we doing it? Wow, boy, this messed up. So we're enabling it using a field message bus. How many people in here use LinkedIn, Facebook, or have a smartphone? Yeah, we all do, right? You all use a field message bus. If you've ever tapped your phone to another phone and shared something, field message bus. You ever seen an update on LinkedIn or Facebook? Field message bus. We're adapting the MQTT system, which is an OASIS standard. I believe it's an OASIS standard. And we're also using DDS, which is a brokerless protocol. To do that, we're releasing open source adapters for vendors' technologies. And we have a website for anybody who's interested, opengridstandards.org. We've got a multi-tiered architecture, and I apologize, I don't have enough time to go through all this, but we do have a tiered architecture that basically allows us to also install security and do a field area network. One funny thing, so when I did my degree in computer science and I was a board intern at Southern Company, and so I decided to hack their network, and I did pretty easily. And I view mesh networks for metering solutions, they're a bit like kindergarten. Essentially, we have one person in control of the whole domain, and a whole bunch of people that keep wanting to touch one another. and spread germs. And really the handy wipes, they're really the only best defense against getting people sick. In reality, where we ought to be going is essentially figuring out a way to distribute that cybersecurity platform. It's the same thing the military does. It's the same thing that Duke is now deploying. We are in an FOA with the government and a couple of companies to deploy a distributed cybersecurity solution that uses the same message bus and the same architecture. Some nerdy stuff about analytics, but the key thing about it is we don't know where to put the analytics, as well as to how to unlock the data, and much of what we're doing is really to federate the data and give us the ability to put it wherever we want it. And last but not least, solid state transformers, my apologies. Probably the next most valuable thing to happen to the grid. See? Don't mind that man behind the curtain. The next most important thing to happen to us that will be coming, it will allow us to do far more work with renewables than we could ever do before. That's the last slide. That's why I threw it. I didn't need it anymore. And anyway, we see the next big thing for us after we federate the data and create these sort of capabilities is solid state transformers. With that, that's the conclusion of my presentation. Happy to take any questions.
Sure. We'll save those till the end of the panel. I'll say a few words, and you might be nervous that the moderator is talking, well, you just have to throw things at me or go to sleep, so I'll know that I'm out of time. Yep, so I added my own name to these slides, although they were the content and the slides were generated by Jeff Taft, but I added my own name, so you'll know that anything said that doesn't make sense or is just wrong is my fault. What's on the slides are these great slides are due to Jeff Taft, and I started on the very same day at PNNL, and during the first week of onboarding process at PNNL, we went through the same 51 meetings, introductions, so we have become blood brothers in the area of grid modernization at PNNL. So this is about control and coordination in a transactive energy environment. Transactive energy, that several of you know, was a term that built on a long scholarly tradition, but the term was coined at PNNL related to a series of very large-scale demonstrations that were carried out that forced PNNL to elaborate further on that due to some issues that have been mentioned, and I'll come back to that. So basically, the grid as we have known it has been based on a number of assumptions that I've listed here. The assumptions have been that the generation is dispatchable, that there's no energy storage of any significance in the grid. Power must always be kept at balance. Generation must always follow load, and the distribution system can be seen as a laminar structure related to the transmission system. These assumptions are now, with the current development, being violated, and there's significant consequences of that, where you cannot just have some bounded fear, but you can mathematically prove that at least some of the directions we are following mathematically will drive our grid to instability and to slowly fall apart. So we need to really do something about that. We have to remember that the grid was not really designed for economic reasons. The purpose of the grid was always to keep the lights on, and that's another premise that we need to look on with new perspectives. So how do we address this issue of kind of joint optimization from control perspectives and economic perspectives? Now we are introducing potentially millions or even billions of interactive endpoints. So the trends we are seeing in the US, and this also applies to, as you mentioned, to Europe and to Asia, is that we are integrating renewables both at the transmission and distribution levels. The utilities see a lot of rotational inertia disappearing, being taken down, or being hidden behind walls of power electronics. We see that we have new markets, including interactive loads and the notion of prosumers. We are changing to much faster timescales. And we see a lot of power electronics, and I would like to stress power electronics are being seen for good reasons as the enemy, but they can also be seen as new opportunities, and I think it's very important to bring that perspective to bear. And finally, we have distributed generation, demand response penetration, and we see a lot of local energy networks emerging, microgrids, where I would like to add the same comments. These are being seen as threats. That is for good reasons, but they are also opportunities, and we should bring that perspective to bear. We have a lot of new grid functions. They are listed here, but I would especially like to mention the integration of distributed generation and demand response, energy storage integration. There's a very significant initiative going on in California and in other places. We are seeing responsive loads, and that's wonderful. Although we heard this morning they can be too responsive. There's definitely challenges in that also. We have issues with grid stabilization, and we see a lot of inverter controls. Those are big opportunities and threats, and we have the microgrids coming in with all the issues with gradients when you connect, disconnect, and so on. And finally, we see load modulation being introduced for, and we heard about that this morning also. So I don't think I need to go into that direction. A significant issue here is the notion of grid coupling and feedback. There's a lot of wonderful literature being described by this. We have to remember, at the end of the day, everything is being governed by the laws of Kirchhoff, and any approach that doesn't take that into account is bound to fail. We also have to become aware that we need to think about how can we make the actual rollout. Having a now and then is not enough. We also have to think about the deployment, and this has a lot of implications for grid architecture, involving how do you design this and how do you control it, where we see architecture as a notion that covers all of that. Another issue is how do we coordinate all of these issues, all of these assets that are becoming available. As the legacy grid does not have a strong multi-tier coordination framework, so this is an issue we need to address. We also have to, as I mentioned, distributed energy resources tends to be seen as a threat and not an opportunity by utilities. I talked to someone recently who works at R&D part of a utility, and when they try to introduce new notions, the general company would say, "Don't bomb our grid with dangerous technology," and that's also for good reasons. So these are the challenges that we are seeing. We need coordination mechanisms, otherwise we cannot introduce any of the new business models. And interoperability is crucial in this, but it's not in itself a complete solution to what we are facing. So there's a number of systemic issues and requirements that we need to address, such as reliability, scalability, stability, security. But these are just a few. In fact, John Doyle at Caltech recently compiled a full list of probably not even a full list, but at least a list based on what recent papers argue to be extremely important aspects ending in ITY that we should address. So that list was much more than these four. That list was 80 properties that we need to ensure. And some of those that might be less obvious is how do we federate, and how do we go about with constrained fusion? How do we disaggregate? What about boundary difference, and what about local selfish optimization? There's been some very important papers that show some of the and this was also mentioned this morning about what if users become too responsive. This is a major issue, and as I've and finally, what about communications? There's a great wilderness out there of different standards. We need to make sure that these become compatible. One approach could be scalar control, and I'll come back to that on this slide. So disaggregation has to be resolved as one vision, where we solve the communications and disaggregations issues simultaneously and make it scalable. There are a lot of, on paper this looks like a wonderful solution, but the question, many questions come up, like the first one being, who's going to pay for this? And another approach is to use scalar approaches, like sending scalar signals to endpoints. That could be just one global common signal that is broadcasted, or location-dependent signals. And other approaches are distribution, locational marginal pricing, transactive energy as proposed by PNNL, and prices to devices. I will say a little bit about these before I close. So if you take embedded markets and prices to devices, I think it was mentioned this morning, the idea is that you take a scalar signal with disaggregation models and use that to achieve scalability. And this is actually an approach that's extremely difficult to do, but can have but potentially could solve the problem. It's very difficult to implement. Another one is embedding the market and use prices to devices models with one market and then a huge number of devices and a delay. This will lead to instability, so this is, without modification, this is simply an approach that is extremely difficult to use. There's a seminal paper by Bruce Behani, and Sean Main has also published on this, and this is not the way to go, at least not in the form it has been proposed. Transactive energy, as defined by the Gridwise Architecture Council, is a number of techniques for managing generation and consumption of flow of power within an electrical power system, relating to market constructs, taking grid reliability constraints into consideration. So transactive might refer to actual economic transactions, but in a more abstract manner to decisions made by values. But the key elements are reliability constraints and control technology based on value in one or more levels of control. And this has to be seen in perspective to network utility maximization. I think this specific model is one proposed by Stephen Lowe and his group, where they use a optimization approach based on a decomposition scale, where they're exploiting that we have a laminar coordination structure. This is an approach that has been proposed by Jeff Taft. So essentially it relies on the same principle as the approach by Stephen Lowe and others, in the sense that it's more general, but it's utilizing a laminar structure. And I think that's one of the messages that I would like to convey. There's in the thinking of the grid, there's an essential laminar structure, and that's in spite of the heterogeneity of the grid, that's what come to our rescue, that we have a lot of laminar structure. Some of the approaches that are in despair of the current challenges we're seeing are being done by utilities is breaking down that laminar structure. And I think that is a very dangerous development that will prevent some of the solutions that could be done in a more systematic approach. So if we combine the idea of transactive energy and laminar framework, we'll get solutions where we can exploit the laminar coordination concept to facilitate transactive energy nodes and use decomposition to map to every kind of real systems of all the huge amount that we see differently in a great diversity on the grid. And very much in line with the previous speaker, what we have to generate is a platform. Once we have a platform, we'll see exactly the same as we saw with the internet. Once the platform is there, we will see businesses emerge that we had no fantasy to envision today. But we have the responsibility to provide the platform. Thank you for your attention, and now I would invite you all to pose questions to the panel, and we only have 10 minutes at most.
Well, I propose that I'll take coffee orders from the speakers, and we go into the break a little bit. But I'll go over and bring some coffee for you guys.
Okay, but we can start the.
Let's please have a discussion. And,
yep. Yeah. So you're welcome to ask individual speakers, or you can ask the panel at large. So please go ahead.
I'll take some cream, Sean.
Black and bitter.
Black and bitter.
One beer.
Yep. So please fire ahead.
Thanks all for your excellent presentation. Very informative. I'm wondering about what you all talked about, in particular you talked about the importance of interoperation and also pushing intelligence into the network. Is there a well-accepted wisdom of whether doing that enhances or detracts from security?
I can start with that. Yeah. Security, do you mean cybersecurity? Or? I don't think there's a lot of experience with that in the utility industry today. When Duke was looking at the problem, we essentially said, what is the military doing? We figured that no matter what, they have more experience doing that than anyone else. And essentially their solution embodies utilizing a field message bus, DDS, and distributed intelligence to identify threats, and then using an extremely low latency messaging platform, tell everyone else using a quality of trust scheme that something is bad, and then to blast that thing away, rebuild it, and re-give it its security credentials. And Duke right now is partnering with the company that helped implement that for DoD and for the Marine Corps. That's a company called Viasat, and then we're also partnered with Southern California Edison. And so the three of us are attempting to do it. SoCal Edison is doing it for transmission. Duke is doing it for distribution.
but together we should have this distributed cybersecurity platform. We've provided 100 and something different use cases of ways to hack and attack the grid, and we are looking forward in about 2.5 years' time of trying them out. But first we've got to engineer and put the system in place.
And I think more generally, one could say that you have to make sure that the right security standards are implemented when you develop interoperable solutions and have the right standards. And in fact, it's certainly possible to do the wrong thing while you're, from a security point of view, while you're trying to attain interoperability. So it requires a separate focus.
Yeah, and the other key part of that is not just the security built into the software or the network itself, but the processes. That's why the risk management process has been articulated to make sure that you go through and look at your whole operations. Who has access to the keys, whether it's hard key or a soft key, et cetera, all those process-oriented things. One of the things that was discovered in the Target stores was that the entry point was the energy management system. And a store manager connected into the energy management system to do some function he did, and then came out of that with the virus, plugged into the retail management part of the system, and voila, the virus took off. So there are different points of entry that have to be examined.
Clearly, decentralization offer a significant threat to the security issues that we have, security measures that we have seen so far. But I think it was an important message that the decentralization and distributed nature that we envisage also offers new approaches to security that will actually give us abilities to enhance, especially with the approach that the question that has been asked in security, in the security community in recent years. You can spend all the money you want on defending the perimeter of a system, but at some point every system is going to have intruders inside. And what do you do with those? And there I think that a distributed and decentralized defense system will have a lot of wonderful opportunities. And so yes, distribution, decentralization is a great threat, but it's also an opportunity to actually to add security to our system.
One important point, though, I think, with respect to cybersecurity is you can't be effective, if you start adding cybersecurity functionality when you're halfway through a development. What's extremely important, and this is for all of us, is when we're developing technology, the cybersecurity part of this needs to be included up front as part of our initial design, And I've seen many times where you get partway into the development, and then you start thinking about it, seriously, and it just doesn't work that way. It really has to be included up front.
I really like this sort of thinking about parallels with telecoms, but I think I'd like to push you all a bit on what is in it for the customer in all of this. I can see the smart grid is a sort of great playground for engineers, but we can end up spending a lot of money on being smart. And actually, what the customer's going to see, because it's not like, and maybe it is a bit more like railroads, where basically there's a backbone infrastructure which is nothing you can do, and the best thing you can do is put up a bit of smart communications around it, so that people get better real-time information about when their train's going to run. But actually, the whole thing's still basically based on a network, which is most of the cost. So perhaps you could sort of try and sell this to us.
I see Rayford coming in selling mode.
That's right. Yeah, so yes, I absolutely think the point is well made, which is what does a customer get out of it? And honestly, I think the biggest problem customers have today is that they don't have choice, control, or knowledge over the system. And so when I was growing up in Savannah, we were
we were dirt poor. We lived in a trailer park, and essentially we had to make choices between food and power lost a lot because we needed to eat. Eating was far more important. And the frustration we felt when the power would go out, other than that we couldn't pay for it, was that we didn't know that we had spent that much money. We had no way to control or know or have any sort of insight, nor did we have a way, if there was a competitive market, to compare the quality of service versus another provider. And so for that, I think a lot of what, at least as I'm envisioning, talking about where we're going with the smart grid, is to enable that control. Now, what I don't mean by that is the control that freaks my wife out, which is when I asked her to read a utility tariff once, she said, I don't ever want to see that again. Right? It's not that customers want to have engineering level control of the grid. There are a few, but most don't. Most don't understand it. Most of it, they don't have that big of a share of their wallet. It's not that important to them. What's important is that they have some simple way to make a trade-off between comfort and convenience or predictability versus price. And that's all they're really looking for, is if you can make it super simple through observation or through some simple mechanism to get that utility function, then let all the rest of the engineers and everybody else figure out all the control mechanisms and everything else behind it. And I think when we're talking about federating data and implementing IT and telecom and these sorts of capabilities, what we're really trying to do is put those systems in place to give them that, so that now that the control and management of the grid can be kind of an afterthought, and now there are new services that could come on top of that, like, hey, I can alert you when I see that your air conditioner needs a tune-up, or hey, I can see that you're a prime candidate for this kind of an offer for a battery or photovoltaics or whatever. These are sorts of things, new products and services we could offer, and we shouldn't be afraid to offer if we implement this technology correctly.
And
Also the integration of, the outage management, your customer management, where instead of you getting angry and having to call the utility to tell them your lights are out, they already know the truck's already rolled, and then they're sending you a text message saying it'll be fixed in 20 minutes, or that proactive way. And that's a significant customer benefit too.
Doesn't come for free. The products being offered, though, when you said we should be able to offer those products, you're still living in a integrated world. What about the work?
No. So the whole, and I didn't get to go in detail on the slides about federating data. So I have to view even though I work for a vertically integrated utility in some states, my view of the world is strictly the network. I honestly don't care who the generator is nor who the demand is. And so my objective function is to make that transaction between supply and demand as efficient as possible, no matter who they may be, whether they are me or whether they are a third party. And admittedly, I spend a chunk of my time in gas and gas pipelines, and pipelines kind of have to treat the world that way, which is, I don't really care who you are. I'm going to do business with you. And to me, that's the way to really make the grid function as efficiently as possible, which is, I will take all comers, I will satisfy all constraints, I will try and make whatever the transaction that is desired as efficient, capable when needed, where needed.
Now and that's great, because that's what, as an ex-regulator, I would expect for open access, so that there's a level playing field competition.
Right.
But I think that one of the concerns is going to be is that when you have utilities getting into potentially the retail markets, competing against third-party suppliers of these types of things, what we're going to have to do is have those rules about affiliate transactions and all of that laid out clearly.
Yeah, and I would add to one other point on that one, which is, I see a lot of regulation today that is meant to be a win-loss situation. And the win is a little win, but the loss is a hammer, is a sledgehammer across the head of the utilities. And if that's the future of regulation, utilities are railroads, right? We won't care, we won't innovate. I'm sorry, customers, you're not going to get very good service. You're going to get okay, we will comply. But if we have every motivation to make profit, to grow, to become the Verizons and whatnots of the world, we will innovate far beyond today's expectations. We have to unshackle those businesses, and we have to set up, I would argue, the right regulations that allow them to do it. But we need both. We can't do, hey, we're going to give you crappy regulation, but we'll give you, the ability to have these rules. We need them both.
And I think that's for Sean, for some of your future discussions, is what do those regulations start to look like? Because without the regulation, modern regulation and modern business plans have to somehow sync together, or we get real cognitive dissonance, I think. And
Yeah, oh yeah, I could probably go on ad nauseum about my perspectives on that, but we'll do it offline and maybe with alcohol.
The question,
Well, there'll be lots of those. I just, the thing is, that I think there's no way, like right today, there's no way you can make a case for any consumer benefit. You know, 'cause I don't think consumers care that much. You know, power's so cheap. So I think unless we're talking about long-term societal goals, you know, this is a waste of time. I mean, the reason we want consumers in the loop is really because we want more renewable energy. I mean, it's just totally wild. We just don't need to regulate anything. So
Once again, I would offer the perspective of someone who had a $300 bill, strip heat, no insulation, and we didn't pay it. We got our power cut off. We were cold or hot or whatever.
Right.
There's a huge amount of benefit.
Yeah, there are definitely certain areas where that's true. I mean, also in certain islands, Hawaii needs something quickly. But in most of the United States, there's no value at all. We're thinking about long term, we're trying to get ready for greater penetration of renewables.
I think the argument is that we're not really on a sustainable path.
Yeah.
And we is not just utilities, it's society at large. And it's not sustainable in the longer term as we think about emissions or the increasing demand for power, and different parts of the world actually have different parameters and criteria there.
and following up on that, should we really see power as a commodity? It has been a tradition that we deliver exactly the same product to every customer, to every price, at every time of every day of every year. And if we could deviate just a little bit from that perspective, it could be that could be a significant part of the solution to the challenges that we have been hearing today. And of course, there are some significant social implications of that we really would need to discuss before we went down that alley. But at least we should have the discussion, because there's a significant interest in that already in the existing society. And I think we should facilitate that discussion, and clearly politicians would need to be part of that. Could we take one final question?
Actually, I want to argue with Sean's comment. And I think actually there's a lot of benefit to consumers, but doesn't have anything to do with the system. It has to do with making their life easier. Okay. I got a new air conditioning system and got some fancy new thermostat. Okay. Why did I like the thermostat? I now touch the thermostat once, and I've got it set for everything I need. Oh, when I go on vacation, I have to hit a couple of buttons to reset it. But I no longer have to tell it heat, cold, any of that stuff. Okay. You know, there's a lot of appliances that we're making sort of smarter and smarter in ways that could enhance things on the grid. But consumers don't care about that. Consumers care about the fact that they can wash their dishes at 3 in the morning when they don't have to hear the noise. And what would really be nice is if somehow we could take advantage of those things for improving the grid and smoothing out demand and things like that.
Go on that.
I think there's some follow.
I'm starting to get into my own presentation tomorrow, so let's wait.
So I guess you have 15 minutes for coffee, right? Yeah.
Okay.
Okay.
Thank you.